Yes, so I'm going to talk today about decentralized identity, and I'm going to focus on a system called Candid, which was developed in my group jointly with Andrew Miller's group and with colleagues at JPMC. But before I begin, I want to talk a little bit about what decentralized identity is and the motivation behind exploration of this area. Nearly all of us have had
Ari, I'm sorry, Ari, but we are not seeing your slides. If you were expecting us to see it, you're not sharing them yet.
Okay.
So you need to share them.
Well, when we tested, I think it was going the other way again. We tested the other speakers and this kicked out our slides. So you just have to start sharing again.
Exactly.
Okay, I just have to restart.
Great.
Is that working?
Yeah, now we can see them. Perfect.
Now you see them? Okay.
Sorry.
So nearly all of us have had the experience of opening a financial account online of some type, perhaps even a cryptocurrency account. And often what you need to do is to validate your identity in a video. You show your face with an identity document that contains your name to prove your identity, but you don't do it like that because then your fingers are covering the identity document. That's no good. And no, you don't do it like that because then the identity document is covering your face. So yes, you want to do it like that, exactly like that, hold still, or you could potentially do it like this. The point is that this process of proving your identity via video in a manual way is cumbersome, and it's also prone to fraud. And this is part of the motivation for exploration of decentralized identity. So what is decentralized identity? The basic idea is as follows. A user to create an identity document generates a public-private key pair, and then an authority known as an issuer creates a credential, as it's often called. This could be an identity document, say a driver's license, if the issuer is the Department of Motor Vehicles, and binds this document to the public key of the user. The user then, if she wants to present this credential or document to a third party, say Alice here wants to take out a loan and she needs to prove she's, say, over 18 and a resident of the state of California, the user does is present the identity document and use the private key to prove that this is indeed her document, to prove possession, ownership of the document. And then she gets her loan or whatever else she's using the document for. This basic idea, this basic approach is, as it turns out, very powerful, something you'll see in the course of this presentation. And the notion of decentralized identity has been embraced by a whole bunch of different organizations. There are several standards efforts afoot in the tech industry to promote its use. One of these efforts is known as the Decentralized Identity Foundation and counts among its members dozens of companies. These include tech companies, of course, but also financial services companies, insurance companies, and so on and so forth. So interest in this basic idea is, as it turns out, quite broad. Why is this interest so widespread? Well, decentralized identity has several goals. One is to improve the experience of a user in, for instance, setting up an account online, to do away with the problems that I mentioned at the beginning of the talk. Another is to help reduce fraud, another problem that I mentioned at the beginning of the talk. There's a challenge involved in ensuring that an identity document presented remotely by a user is authentic. And this is something that decentralized identity can help with. Another slightly more subtle benefit of this approach is that it empowers users to manage their own data. Notice that Alice, in presenting her identity document to take out her loan, had to initiate the process of sending the relevant data to the bank. She controlled her identity document, she controlled whatever sensitive information it contained. And this control can extend to other credentials and to a wide range of sensitive data. Additionally, with decentralized identity systems well in place, it would be possible in principle to issue credentials relatively straightforwardly to disenfranchised persons, stateless persons, refugees, and so on and so forth. Aid organizations could easily issue identity documents. Why are enterprises, though, particularly interested in this technology? All sounds good for users. Why are enterprises signing up for standards efforts like the Decentralized Identity Foundation is creating? Well, a benefit of having users control their private information is that that information doesn't need to be stored by service providers. And this reduces the liability of enterprises that would otherwise have to handle the sensitive data, in particular liability in the case of a data breach. This all sounds good, but there are a couple of critical problems swept under the rug in pretty much all of the standards efforts we've seen in this space. The first is the problem of this issuer here. Right, so I said an issuer, like the Department of Motor Vehicles, creates a digital document, identity document, and binds it to the public key of the user. But where are these issuers going to come from? Right? It's unlikely that the Department of Motor Vehicles in the state of California is going to become an issuer of decentralized identity documents until there's a decentralized identity ecosystem in place already, right? Until there are users of these documents. But on the other hand, there can be no users of decentralized identity until an ecosystem has been created. So in effect, we have a chicken and the egg problem here. We're not going to have issuers until we have users. We're not going to have users until we have issuers. This is one key problem and one key obstacle to the realization of decentralized identity. A second challenge is that of key management. But we know that users have a great deal of difficulty managing their secrets, passwords, for instance. Now, this is perhaps doubly true in the case of private keys. Just one data point here. It's estimated that something like 4 million Bitcoin, and I haven't checked the price of Bitcoin the last 2 minutes, so I don't know how much this is worth, but say 160 billion or so, has vanished forever because people have lost their private keys. Just this past month, there was an article about a man who lost 7,500 Bitcoin as a result of the storage of his private key on a hard drive he'd thrown away, and he was appealing to his to town hall to allow him to trawl the local garbage dump to try to recover this hard drive. But this problem is pervasive. In fact, the key management problem is so challenging that what we see is centralized financial systems becoming decentralized in many cases through Bitcoin and other systems, which is very nice. But then users, because they don't know how to manage their private keys, or I should say, because it's so challenging, making use of services like Coinbase. In other words, re-centralizing what was supposed to be a decentralized system and undermining the very value proposition of a system like Bitcoin. Yet another problem that gets swept under the rug is the challenge of ensuring that a decentralized identity system is Sybil resistant. We want it to be easy for users to obtain identity documents, but we don't want it to be too easy in the sense that we don't want a single user to be able to obtain multiple distinct identity documents, or to obtain different instances of the same identity document in such a way that the user can pose as multiple people. This would be problematic as well, particularly in applications like voting. So that's just to give you a flavor of what decentralized identity is all about and what the main technical challenges are. Before I discuss our solution, the Candid system, I need to talk about a critical building block called DECO. And I'll do this at some length because this really is the cornerstone of Candid, the system I'll discuss later. Right. Here's the problem that DECO attempts to address. Let's imagine we have our two canonical characters here, Alice and Bob. And Bob in particular has created a new token called Bob's Bubble Token that he would like to sell in an initial coin offering. Alice comes along and she'd like some Bob's Bubble Token. But Bob is a conscientious guy. He doesn't want just anyone buying his bubble token, and in particular, anyone who doesn't really have the financial means to participate in the ICO. So Bob requires that in order to participate, you need to have at least $5,000 in liquid assets. Alice here goes online, looks at the balance of her bank account, discovers that indeed she has more than the requisite amount. She has more than $5,000. So she says to Bob, you know, I have more than $5,000. I'd like to participate in your ICO. Bob's natural response is, okay, that's great. Can you prove that you have a balance of more than $5,000 in your bank account? Well, Alice can try to do this in a number of different ways. One is to send Bob a screenshot of her account. But of course, this doesn't work terribly well, right? Because screenshots can easily be manipulated. Alice can Photoshop her balance up to whatever amount she wants. So this simple idea obviously doesn't work very well from a security perspective. Alternatively, Alice could send her credentials, her username and password to Bob so that he can log into her bank account on her behalf and check her balance directly. This would work from an integrity standpoint, data integrity standpoint, in the sense that Bob would indeed be able to determine Alice's true balance. But it has another problem, namely that this isn't a good way for Alice to keep her balance above $5,000. Right? Bob can just steal Alice's money. What we would like ideally is Alice to be able to get a proof of some kind from the bank server that she can present directly to Bob. And it would seem like we should be able to do this because when you log into your bank account online, you're connecting to the bank over a secure channel, over TLS. Right? And this channel makes use of public key cryptography and a protocol that ensures data integrity and confidentiality between the user and the bank. So with all of this cryptography at play, and particularly public key cryptography, it would seem like Alice should somehow be able to construct a proof for Bob. The problem is that although the key exchange in TLS makes use of public key cryptography, the exchange of data in the record layer makes use of symmetric key cryptography. In other words, Alice and the bank actually share the keys that are used to secure the data. For example, to ensure integrity, the data may be MAC'd. Right? There may be a message authentication code, symmetric key signature attached to the data. And this effectively means that Alice is equally able to create valid looking data on this channel as the bank is. So forwarding TLS data to Bob is basically no better than a screenshot, as we can't take advantage of the security in this secure channel. So another approach that's been proposed to the construction of proofs of the type that Alice would like here is to modify TLS. Right? Because of the use of public key cryptography in the key exchange, because of the use of public key cryptography for Alice to determine that she's actually communicating with the bank, servers already have certificates. And they can, in principle, digitally sign data using the private keys associated with those certificates. Right? In fact, they do for the key exchange, typically. So various approaches to modifying TLS to take advantage of this fact have been proposed. A very nice one from ETH Zurich called TLSN, for instance, suggests modifying the server to allow for digital signing. OpenID Connect does this in practice. Unfortunately, only to a limited extent, only for certain types of data and with limited forms of privacy. The problem with this approach in general is that it requires big infrastructure changes. It would be very nice to have digitally signed data emitted by TLS natively, but this isn't likely to happen in the near future. And in consequence, the data we would really like to have in a decentralized identity system is often locked up. Right? You can't prove to somebody directly that your bank account balance is above $5,000. You can't present your driver's license in digital form. You can't present data like a credit score, right? All of this is essentially sitting behind a wall somewhere. All the data are siloed as a result of the way that TLS works. Our approach to this lack of accessibility for private data today is a system called DECO. The idea is as follows. A user like Alice can connect to a server over TLS and then prove things in zero knowledge about the content of her session with the target server. So for example, Alice can log into her bank and prove to Bob in zero knowledge that she has more than $5,000 without actually showing her bank account balance. Right. But didn't I just say that TLS can't do this? We sidestep the lack of a native capability of this kind in TLS in the following way. Let me show you what's going on under the hood. The key idea is something known as a three-party handshake. And the basic idea here is to split the session key between two parties, a prover and a verifier, rather than the user, as in the typical scenario, holding this key entirely herself. The key will be split between the prover and verifier for reasons I'll explain in a moment. Normally in a TLS key exchange, the client, Alice here, generates her own private key, just in some versions of the protocol, and a corresponding public key. And she presents this public key to the server for the key negotiation. But she, as I said, she holds this private key herself, and she obtains a session key to be shared with the server. In the three-party handshake, what happens is the following. The verifier, Bob in our scenario here, generates his own private key and corresponding public key, and he sends his public key to the prover. The prover then generates her own private key, and she combines her private key with the public key that Bob has presented to construct a joint public key. What we get out of this is a private key, X here, that is the sum of private keys held by the prover and the verifier. In other words, we have split the private key that the client, in the view of the server, is presenting to the server for key negotiation. And the result of this is the following. Alice and Bob can now generate a shared session key for the TLS session, which the server holds in its entirety. And they can use this key, this session key, in a secure manner. For example, they can decrypt data sent to Alice, provided that they cooperate. They use secure two-party computation in particular. I won't get into the details here. They can jointly decrypt data intended for Alice. But Alice has no way now of forging data, a piece of data D, from the server. I mentioned that in the standard usage of TLS, Alice holds the key K and therefore can forge data because she can construct a match MAC. She can't do that now because she doesn't actually know K. Okay? Again, through cooperation, Alice and Bob can do things like enable Alice to prove facts about this piece of data D, and she can do this in zero knowledge desired. A really important observation here is that this process of splitting the key on the client side between Alice and Bob is transparent to the server. There's no modification to TLS, and the server actually has no idea that this joint protocol is taking place. This two-party protocol is taking place between Alice and Bob in the background. As far as it's concerned, It's just talking to an ordinary client, just talking to Alice in particular. Right. This approach gives us a somewhat refined picture, or enables a refined picture of how DECO works. Right. Alice and Bob now engage in a three-party handshake when Alice sets up a session with the bank. And when she receives data from the bank now, she can send a zero-knowledge proof to Bob about facts regarding the data she's received. That's in the case where Alice is just trying to prove something to a single verifier, Bob. This concept is even more powerful when you consider its use with a committee of verifiers, like an Oracle network in the blockchain setting. Now what Alice can do is log into her bank account and prove things individually to all of the nodes or some subset of the nodes in the network. This subset of nodes, having received a proof from Alice that her bank account is above $5,000 in this example, and these nodes can sign a statement to that effect. They can jointly sign a statement to that effect that becomes a decentralized identity credential. So this network can verify that something Alice is claiming is true and enshrine that truth in a document that Alice can then present to third parties like Bob or a bank from which she wants a loan. Now, DECO operates on a purely cryptographic basis. There's an alternative way to achieve something very similar. We take this alternative approach in a system called Town Crier. What Town Crier does is use trusted hardware. It's called a trusted execution environment. For example, Intel SGX, as a way of enabling the user to construct a trustworthy decentralized identity credential on her own. And the idea in a nutshell is that within Town Crier, a system like Town Crier, you can run an application that is tamper-proof. Alice can log into her bank account through this tamper-proof application. She can do so without revealing her credentials, without allowing them to escape this protected environment. And because the program is tamper-proof, any attestation it emits, any credential it emits, is trustworthy in the sense that a third party knows, provided that SGX provides all the security guarantees that it's supposed to, that the credential was issued by this particular program. Assuming then that the third party trusts the code, the credential is trustworthy. The only problem with this approach is that you need to trust trusted hardware in order for it to work. And there are many because of weaknesses recently evinced in SGX that don't like trusted hardware. But for those who do, this is a more direct and more efficient approach to achieving the same goal. Okay, so at this point, having gotten the building block out of the way, I can discuss Candid. Candid involves the use of a committee, a collection of nodes in some network, like an Oracle network, for instance. And we assume that some fraction, a majority fraction, say, 2/3 fraction, are honest. This committee, we presume, has the ability to store secrets securely. And this can be done via secret sharing. So secret can be parceled out among the different nodes in the network. Another goal of the committee is to verify proofs of the type that you saw emitted by Candid. So now the credential issuance process can look something like this. Our user now goes to any number of existing websites, like the Department of Motor Vehicles, Social Security Administration, bank, or whatever, logs in, views information of the type she would like to use to prove something to the committee, and then proves to all the members of the committee, or at least some requisite subset, some quorum, the thing she would like to prove in zero knowledge. Right? She doesn't present all the data she receives directly. She just proves in zero knowledge that the data she receives from these authoritative sites supports her claim. And the committee, if these zero knowledge proofs check out, can jointly construct, jointly sign using threshold signature or individual signatures, a decentralized identity document on behalf of the user. The beauty of this approach is we can turn any web server or collection of web servers, as in this case, into an issuer without making any modifications to those servers. So in principle, we could launch this system today without requiring cooperation from the Social Security Administration or the Registry of Motor Vehicles or any of the other sites that the system uses. In fact, they can be completely oblivious to the fact that users are leveraging data from these sites in order to construct decentralized identity credentials. Another nice feature of this system is that the committee only learns the data that the user wants the committee to learn. In this case, for example, Alice can prove she's over 18 to the committee and present a zero knowledge proof based on received data without actually revealing her birth date. The committee learns only that she's over 18. We get legacy compatibility. As I said, there's no need to modify any of the servers participating in this protocol. And additionally, we can construct attestations or decentralized identity documents of essentially any type we like, as long as there's an authoritative website somewhere out there with the data in question, we can construct a decentralized identity document using that data. Now, unfortunately, DECO is not blazingly fast. It is practical to construct credentials of the type that I described, but it does require some work on the client side. And these are figures that are subject to considerable improvement, particularly with various performance security trade-offs. Because the two-party computation is an offline and online phase, I present the figures here in split form. And also we'll mention that much of the bottleneck here is bandwidth. That if you're operating on a slow connection, internet connection, for example, 5 megabit per second connection, then the offline phase of the DECO protocol can take a number of minutes, 8 to 10 minutes. If you're on a fast connection, because as I said, the bottleneck is bandwidth here, then the offline phase can take just a matter of seconds. The online phase, as you see, itself just takes a number of seconds. And as I mentioned, if you're willing to use trusted hardware, all of this can be blazingly fast. Well, you remember that another challenge I mentioned for decentralized identity to achieve fruition is the challenge of key management. So Alice gets these decentralized identity credentials, but she's got to manage the private keys associated with these credentials. And as I mentioned, users are not great at managing private keys. Candid also provides a vehicle to help users manage their private data in a more seamless way. The idea is the following. When Alice registers with the Candid system, she provides her private key to the committee in secret shared form. And the committee will store her key on her behalf. Because it's in secret shared form, of course, no individual node knows the key. And then she registers accounts held by her with a number of service providers of her choice. Could be Twitter, Facebook, Google, whatever service provider she likes. And she provides to the committee a proof that she's able to log into these target accounts. Now, if she loses her key, she can repeat the process. She can log into the accounts that she's registered with the Candid committee and prove nothing but the fact that she's able to log into these registered accounts, and the committee can furnish her private key for her. So in the normal course of usage, Alice might have her private key stored on her phone. If she loses her phone, drops it in a puddle, for instance, all she needs to do to recover her key is log into a collection of accounts that she has pre-registered. And of course, she can do this in a threshold way. She might register these 3 accounts, but require that she successfully log into only 2 of them to recover her key. And the user herself can set this policy. We could accomplish something very similar using, for example, OAuth. The problem with OAuth is that it reveals an account identifier that we would prefer the Candid committee not have, because this account identifier can be used to link a Candid account in that case to a user's real world identity. That's something we would like to avoid for the sake of privacy. Thus, DECO seems better for this purpose than OAuth. We can also achieve with Candid the Sybil resistance that I mentioned before that is so important for applications like voting. The main approach that we take to achieving Sybil resistance is what we call the unique ID approach. We presume here that users have access to some type of unique identifier. For example, a nationally issued numerical identifier like a social security number. And what the Candid committee does is ingest this number presented by the user in a privacy-preserving way, apply a PRF, pseudorandom function to it using secure multi-party computation, and generate a privacy-preserving identifier that can be used to deduplicate users. So when Alice goes to register with Candid, she presents her social security number in a privacy-preserving way. It's secret shared across the committee. Committee applies a PRF to it using secure multi-party computation, and out pops some derived value that can be placed on a registration list. Whenever a user registers with the system, the resulting PRF value is placed on a list that's known to the committee. And now, if the same user tries to register twice, she will end up presenting the same unique identifier twice. You only have one social security number, at least most people do in the US. Present the same number twice. The Candid committee, the second time, will derive this PRF value from the presented social security number and can check it against the list of registered PRF values. And if it's already there, the committee knows this user has previously registered. So we get deduplication, and at the same time, no committee member learns Alice's social security number. Now, not everyone has a unique identifier issued by a national authority. So another approach that we have built into Candid, which I won't get into in detail, is what you call the fuzzy matching approach. So the idea here, and we're all familiar with the challenge of matching misspelled names to previously registered ones. The idea here is that a user relies on name and address, nationality, other types of collection of information that's used in a number of contexts to identify users uniquely. For instance, sanctions lists, essentially financial blacklists, will include this information for target individuals. And because biographical information is prone to small errors, you see some examples here, courtesy of Starbucks, matching the name presented by a user to an identity system with a registered name or other information has to be performed in a fuzzy way. And we have to take these small potential errors or misspellings or inconsistent transliterations into account. A natural notion of fuzziness here would be something like edit distance. So we consider a user's presented name to match a registered name if the edit distance is below some predetermined threshold. It's relatively easy to compute edit distance if you're not concerned about privacy. If the names of all the users who'd registered with Candid and their addresses and so on and so forth were known to the committee and were presented in the clear to the committee at the time of registration, it would be easy to implement this approach. The challenge is implementing it with privacy. And this is something we need to do using secure multi-party computation. That's the approach that we take in Candid. Right? So when a user attempts to register, the user presents her name in a private form secret shared form. The committee has a list of, again, in private form, of all the users that have previously registered, and secure multi-party computation is used to determine whether there's a fuzzy match, a match to within the predetermined edit distance tolerance between the presented name and the registered name. A similar approach can be used for things like accountability. What I mean by that is having users prove at the time that they register that they're not on target blacklists. And in this case, we can use a zero knowledge proof rather than secure multi-party computation. So for instance, if Scrooge McDuck wants to register with the Candid system, what he can do is construct a proof that his name is not present on a given blacklist, like the OFAC sanctions list. Right? And he can do this non-interactively and present the zero knowledge proof to the committee to show that the committee can register him without any sanctions violation. I have just a couple of minutes left. I wanted to mention very briefly an example application for decentralized identity that I can imagine coming about in the fairly near future. Today, decentralized finance loans are typically over-collateralized. That means that to borrow a certain amount, say $100, you need to provide a smart contract with an excess of that amount in cryptocurrency. If you want to borrow, say $100 in stablecoins, you would have to deposit $150 in ETH in a system like, say, MakerDAO. The question is, why is this useful? Why not just sell the deposit? It turns out this is good for leverage. In particular, if you believe the price of ETH is going to rise, what you can do is deposit some ETH, withdraw some stable coins, buy more ETH, get more stable coins, and rinse and repeat until you get a factor of 2 or 3 leverage. But so this is all very useful, but it's really only useful for obtaining leverage, for long bets on the target cryptocurrency. It does have the advantage of not leaking much sensitive information, right? No more than the basic blockchain or cryptocurrency does. Conventional bank loans today, on the other hand, are typically under-collateralized. That's to say that the value of the assets you provide to secure the loan is less than the value of the loan itself. The nice thing is that bank loans can be used essentially for any purpose, right? To buy a house, to buy a car, so on and so forth. But the approval process is slow and laborious, and it involves sending lots of sensitive data around. Here you see a checklist of the documents you need to provide to take out a mortgage. Providing these documents, for anyone who's gone through the process knows this, is extremely onerous. There's a movement afoot to create a form of decentralized finance loan that is under-collateralized. Looks like a conventional bank loan, but operates in the DeFi world. There are companies like Teller and LendDeFi, probably others. These are the only 2 that I'm aware of that are attempting to do this. What they do is they ingest data from a would-be borrower, analyze in the cloud, and then the lenders in a lending pool vote on whether or not to grant the loan. Now, in principle, the data are analyzed in the cloud and lenders just get a digest of the result. Sensitive data doesn't get leaked to the lenders, but somehow the data needs to get to the cloud. It needs to get there in an integrity preserved form. And additionally, this sensitive data is sitting somewhere. It's sitting in the cloud. It's sitting in software that's been created by the company or organization that has created this lending platform. Decentralized identity can help address both of these questions. Right? In particular, you've seen how systems like DECO and Candid can enable users to get data into the cloud in a way that preserves integrity. And you've also seen how users can provide credentials that are just digests of essential information. A user could provide a credit score, for instance, that was computed according to an algorithm specified by one of these protocols without providing the inputs explicitly to the cloud. So decentralized identity can address both the challenges of integrity and privacy here. I'm out of time. I just want to show you some photos of the Candid team here and emphasize that Jasleen Malvi and Deepak Maram, whom you see circled in yellow here, led the project. Candid is hot off the presses. It just appeared yesterday at IEEE Security and Privacy. If you're interested in learning more, you can visit my website. You'll find both the Candid and the DECO papers. Thank you.